This is Bob Capetta from the University of Illinois at Chicago, and this lesson is on constructing functions from graphs. So we're looking at a function in red that appears to be a line. If we want to get the function of a line, we need to know the slope and the y-intercept. So what do we have for this information on this problem? To find the y-intercept, we find out where the line crosses the y-axis, and we can see that happens at 5. So the y-intercept is 0, 5. And then the next thing we need to find is our slope. So remember, we use the letter B to represent the y-intercept and the letter M to represent slope. Slope is rise over run. From this point to this point, we are dropping 2 units, rise -2, run 1 unit. Rise -2 units, run 1 unit. Slope is rise over run, -2 over 1. The slope that we have here is going to be -2. So I have m and I have b. The equation of a line is y equals mx plus b. Making the substitution, plugging in a -2 for m and a 5 for b, and we're going to consider this as a function. So it will be f of x is mx plus b, f of x is -2x plus 5. Of course, there are several functions that are not lines, and we need to have other strategies to identify the equations that define those functions. So the example we have here is a parabola. You'll notice that it's moved away from 0, 0, but if we're starting at the vertex, what do we have? The shape of this parabola is the same as the shape of x squared. Over 1 up 1, 1 squared is 1, over 1 up 1, over 2 up 4, 1, 2, 3, 4, over 2 up 4, 1, 2, 3, 4, and it would similarly be over 3 up 9 if we had enough room. So the shape of this graph is y equals x squared, but it has been moved off of the origin. How far has it been moved? It appears as if it is moved over 1, 2, 3 places to the right and 1 place up. So how do we start with y equals x squared, shift 3 to the right and 1 up? What will our strategy be? Well, of course, we remember that f of x is x minus h squared plus k, shifting h right, k up. H shifted 3 units right. We're going to have x minus 3 squared plus 1 unit up plus 1. So that is, again, the shape is y equals x squared with those shifts, and we have our function written that way. Another sort of a parabola is this. So we look at the x-intercepts. We have an intercept at 2 and an intercept at -3. Those are zeros of the function, and we're also given the y-intercept up here at 0, 18. So can we find this function? Well, we start with the zeros. 0 at -3, 0 at 2. So I like to think about x equals -3, x equals 2, and then rewrite those things as equations equaling 0. So if x equals -3, this is 0, x equals 2, this is 0. We're going to rewrite this as x plus 3 is 0, x minus 2 is 0. And those are going to be 2 of the factors in our function. Now, these zeros have multiplicity 1 because they penetrate the x-axis. If they bounce, they have multiplicity 2. If they flatten out and continue to go the same direction, they have multiplicity 3. So keeping this in mind, we now think of the following. F of x equals some multiplier z times x plus 3 times x minus 2. And our goal will be to solve for z, and that will go ahead and give us the function defined by this graph. Now how about f of 0? Plugging 0 in here, we get z times 0 plus 3 times 0 minus 2. 0 plus 3 is 3. 0 minus 2 is -2. Multiply those together, we get f of 0 is -6z. But we also know what f of 0 is up here. That is our y-intercept. So in that case, we have f of 0 is 18. Putting these things together, -6z would have to equal 18, or z would equal -3. So going up here, if we plug -3 into that, you will see that we have f of x is -3 times x plus 3 times x minus 2. Notice this is an order 2 polynomial with a negative leading coefficient. Multiplying all this out, it would start with -3x squared. Even, negative, down to the left, down to the right would be the end behavior. Okay, now take a look at this example. We have a 0 at -2, a 0 at 1, and a 0 at 3. But the 0 at -2 has multiplicity 2 because it bounces. So if x equals -2, we can think of that as x plus 2 equals 0. But since it has multiplicity 2, it's bouncing, we're going to consider that as x plus 2 squared. That needs to show up in our answer. Same thing with 1. X equals 1 bounces. x equals 1 has multiplicity 2. Let's subtract 1 from both sides. So x minus 1 has multiplicity 2. X minus 1 is 0. With multiplicity 2, we'll consider that x minus 1 squared. Now this piece here, our next 0 is 3, but that only has multiplicity 1. It penetrates the x-axis. So we have x equals 3 is a 0 with multiplicity 1. So x minus 3 equals 0. And then we'll really think of that as x minus 3 to the first power. So putting all of these things together, x plus 2 squared, x minus 1 squared, x minus 3 to the first, with a multiplier in front, we've got to find that multiplier. Now counting these things, 2, 4, 5, this is an x to the fifth polynomial. It's odd polynomial. If it's down to the left and up to the right, we know that z is going to have to be positive due to the end behavior. But we can go ahead and we can calculate z, so let's do that. This is what we're working with. And plugging in 0, 0 plus 2 squared, 0 plus 1 squared, 0 minus 3. 0 plus 2 is 2, squared is 4. 0 plus 1 is 1, squared is 1. 0 minus 3 is negative 3. Multiplying all that together, we get f of 0 is negative 12z. But what else is f of 0? We look at our picture here, we have 0, negative 24, so f of 0 is negative 24. Therefore, negative 12z would have to equal negative 24 since they are both f of 0. Dividing by negative 12, we get z equals 2. And as I mentioned, we knew if it's down to the left, up to the right for an odd polynomial, the leading coefficient must be positive. So our final answer requires us to plug that 2 into this f of x. So that we're going to get f of x is 2 times x plus 2 squared, x plus 1 squared, x minus 3. But notice in our example so far we haven't had vertical asymptotes. So that adds to the challenge a little bit when that happens. So let's look at our next example. Vertical asymptote at negative 1, vertical asymptote at 2, and a horizontal asymptote, it looks like at y equals 3. So do we have enough information to be able to work on this? And as far as this vertical asymptote at negative 1, it's going down on one side, up on the other. When that happens, it's multiplicity 1. Same thing with 2. Down on one side, up on the other. When that happens, the multiplicity of the asymptotic function is going to be 2. It's going to be 1. That's order 1. It's order 2 when they're both going in the same direction, which we'll see here in a following example. All right, zeros. Crosses the x-axis at negative 2, crosses the x-axis at 1, penetrates, it doesn't bounce. So those both have multiplicity 1. So if x equals negative 2, that means x plus 2 is 0. If x equals 1, that means x minus 1 is 0. So we're going to need in the numerator a factor of x plus 2 and a factor of x minus 1. So on top, our f of x is going to use those pieces. Now regarding the vertical asymptote, I have one at negative 1 and one at 2. So that'll be division by 0 at these values. If x equals negative 1, x plus 1 is 0. If x equals 2, x minus 2 is 0. So the two factors we're going to have there are going to be x plus 1 times x minus 2 in the denominator. The previous situation, those are going to go in the numerator. So here were our zeros, x plus 2, x minus 1. Those are in the numerator. They make the function equal to 0. The vertical asymptote factors, x plus 1, x minus 2, go downstairs. They make the bottom 0. But I have some kind of a multiplier that I'm going to need to figure out. But that I can get from the horizontal asymptote. So let's go back and look. We have a horizontal asymptote here at y equals 3. So the ratio of the highest power of the top to the highest power of the bottom should be 3. If we multiply everything on top, we're going to get x squared plus stuff. Multiply everything on the bottom, we're going to have x squared plus stuff. So the highest power of the top is x squared, the highest power of the bottom is x squared. Therefore, z is going to have to be 3 to be able to give us that horizontal asymptote at y equals 3. So knowing z equals 3, we can rewrite the function f of x as 3 times x plus 2 times x minus 1 over x plus 2, x minus 1. Using the zeros, we got x plus 2 and x minus 1. Using the vertical asymptotes, boom, boom, we got x plus 1 and x minus 2. Using the horizontal asymptote, we're able to get z equals 3. Okay, now this one's different. 0 is at negative 1. I have the x-intercept there, 0, negative, and 9th, identified. I have two vertical asymptotes, one at negative 2 and one at 3. But notice at 3, the function's going down on both sides. That's going to make that an order 2 asymptote. But let's think about the zeros first. We have a 0 at x equals -1, and it's not quite flattening out. This still only has multiplicity 1, not quite flattening out. So if x equals -1, x plus 1 is 0. With multiplicity 1, we're going to think of it as x plus 1 to the first in the numerator. No other zeros. Asymptoting this way, down, asymptoting that way. All right, so the top is going to have an x plus 1 to the first power times some multiplier that we need to find. Now, how do we figure out the denominator of this function? We look at the vertical asymptotes. That will be our key. So I have a vertical asymptote at -2. That has multiplicity 1. If x equals -2, x plus 2 is 0. X equals 3 has multiplicity 2. X minus 3 is 0. That'll be x minus 3 squared. So from this guy, x equals -2, x plus 2 to the first. The multiplicity 2 asymptote is because both sides are heading in the same direction. They're both heading down. For a multiplicity 2 asymptote, both sides converge on the same vertical asymptote rather than going in opposite directions. So the last thing we've got to do is we've got to solve for z. The fact that I know that we have 0, -1/9 will enable me to do that. And the horizontal asymptote here would be the x-axis because the bottom is degree 3 when you multiply it all out. The top is degree 1, and in a bottom-heavy fraction, you always have a horizontal asymptote at y equals 0. So what are we going to do? We're going to plug in 0 for x. 0 plus 1 to the first, 0 plus 2 to the first, 0 minus 3 squared is our f of 0. So what do we get here? 1, 2, 9. 0 minus 3 is -3 squared is 9. So f of 0 is z times 1 over 2 times 9. F of 0 is 1/18 of z. But what else is f of 0? Looking at this, f of 0 is -1/9. When this crosses the y-axis, the y value is -1/9. So from this point, f of 0 is -1/9. So again, we know before f of 0 is 1/18 z. From our graph here, f of 0 is -1/9. If both of these things equal f of 0, they have to equal each other. So 1/18 z equals -1/9. Let's multiply both sides by 18 to solve for z. 18 cancels. On this side, 18, -18 divided by 9, z is -2. So all I've got to do to finish this is to put the z of -2 up here, and we have a plausible function for this graph. And that will conclude this lesson.